Hola, I'm John Maloney, creator and lead developer of MicroBlocks, and I'm delighted to be participating in Robolot for the third year in a row. It's great to have the opportunity to work together with friends and colleagues from Spain, including Victor, Jose, and Nina from CityLab EduTech Group, Joan and Josef from the Ministry of Education, Tony Moreno and Miguel, and others in Spain. It's also great to spend time with Jens and Yutka from the Snap team and to meet Camilo for the first time. I want to thank Tony Moreno, Faber Residencies, Joan Gillen, and everyone else who's worked so hard to make this possible. Well, I have a lot of exciting things to share about MicroBlocks 0.5, so let's get started. Some microcontroller boards, such as the CityLab ED1 based on the ESP32 processor, have a device called the Digital Analog Converter, or DAC. The digital analog converter allows you to convert numbers into a varying voltage, which can then be fed to a speaker. I've created this project called Sound Generation that lets you explore different waveforms that you can make using the digital analog converter. Let's hear what some of them sound like. Here we have a square wave. That's actually a wave you can generate without a digital analog converter, just by turning a digital pin on and off. Let's hear some other examples. A sawtooth wave. Notice that that wave ramps up gradually. That's something you can't do with just a digital pin. Here's a pulse train. And a triangle wave. And finally, a sine wave. The sine wave has the least overtones of all. It's just a pure pitch. The last thing I want to show is what happens if you put a bunch of random numbers into the DAC. Yep, you get noise. Random in, random out. Hope you'll explore this project. It's in the By Boards section of the examples under the ED1 and M5 stack. The digital analog converter allows you to synthesize sounds. In this project, we're synthesizing the sound of a plucked string using an algorithm called the Karplus-Strong algorithm. The algorithm is very simple, and as you can see, this program is short. And this program is not only synthesizing the sound, but as you'll see in a moment, we're going to display the waveform as it's being synthesized. But first, let's just take a listen. And now let's take a look at what it looks like on the ED1 screen. In this project, I used the basic pluck sound you just heard, but I made it possible to play multiple plucks at the same time so that you can get chords. I also arranged for the starting times for the notes of the chord to be slightly different so that you get the sound as if you're strumming a guitar or a ukulele, an arpeggio. Let's hear what that sounds like. If I slow the strum speed down a little bit, it sounds as though you're stroking the strings of the guitar or ukulele a little bit more slowly, like this. And finally, I can actually speed up the strum and use minor chords to get an effect like this. So that shows that there are a lot of musical possibilities for the pluck sound in particular, but also for the DAC as a general musical tool. I'd like to tell you about a new feature of MicroBlocks 0.5, which is the ability to access files on ESP-based boards such as the CityLab's ED1. Let me show you. I'm going to first import the file library. And to add something to a file, you first have to create that file. So I'll do that by opening a file called data. And what I want to do is add, it's just some kind of data to it. So I'll use a for block to add the numbers 1 to 10 to this file. So I can just do that by saying I want to append I from 1 to 10 to the file data. And when I'm done with all of that, I'm going to close that file. So let me go ahead and do that. And that happened already. It's so fast you didn't even see anything happen. But let's see if we actually got some data. So to do that, what I want to do is I want to go through the file until I'm at the end of the file. So again, I'll open a file. I will repeat until I get to the end of that file that I want to say the next line of that file. So let's say the next line of the file, and the file in question is data, so I'll just fill that in. And optionally, I could duplicate this block and close the file at the end. When you're just reading a file, it's not as important to close it, but let's take a look at what we get here. Wow, that was fast. So that was the numbers from 1 to 10. Maybe I can slow that down a little bit by putting a short wait in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. Let's see how big the file is. So if I take a look at the size of the file, it's 21 bytes, and I can actually look at what those raw bytes are with this block. Oops, I actually have to open the file before I can look inside it. Open, give me the next 100 bytes. So this is the ASCII representation for 1, carriage return, 2, carriage return, 3, carriage return, and so forth, all the way up to the number 10, 1, 0, carriage return. Okay, so that's saving basic stuff in a file. Oh, I can also list files. Here we go. So there's the file data. I only have one file. I can also get information about the file system. So I've used 3,765 bytes out of about 2.8 megabytes. That's how much is on the flash chip in my ED1. Okay, what could you do with files? Well, you might store reminders of things to do or phone numbers, so text. You might also store media such as images, sounds, or sequences of notes that you wanted to play. But one of the most exciting things, I think, is that you can use files to store data that you collect for some kind of a science experiment. So I'm going to look at that right now. So to do that, I'm going to actually modify this program. We're going to use data, but instead of storing just a number, what I want to do is store some data from the accelerometer. So let me import the basic sensors. And we have here a number called acceleration, which when the microcontroller is just sort of sitting around, it's always measuring. It doesn't matter, I'm just changing the orientation, but it doesn't matter what the orientation is, it's always measuring the acceleration of gravity, which is about 50 on our scale. So I'm gonna basically be storing that data. In this case, I don't want to just store 10 values, but I want to store more values. So I think what I'll do is I'll store, say, 500 values of the acceleration. And I'll also want to close the file at the end of this, so I'll keep that. I only want to trigger it, well, first of all, I want to trigger it sort of when I'm ready to do the experiment. So here's the experiment I have in mind. We know that when you're in free fall, such as when astronauts are in training and they go on the parabolic airplane rides, they're basically in free fall, and it feels like they're weightless, even though they're within the Earth's atmosphere. They're not in orbit. So for a couple of minutes on those flights, they call the flights the vomit comet because people often get sick. On the vomit comet flights, they're weightless and they float around. So I'd like to sort of simulate that weightlessness. So that would be an acceleration of 0. And I'm going to simulate that by throwing the microcontroller up in the air and recording the data while that happens. So first of all, I'll start the process by clicking the A block, but I don't want to waste these 500 samples on data where it's not doing anything. So I'm actually going to trigger it only when it actually accelerates a little bit as I throw it up in the air. So I'll say when the acceleration is above the sort of base value, which is around 50. So let me just guess that maybe if it's around 70, this is going to be the beginning of throwing it up in the air. Okay, cool. So let me go away and try that. Okay, I'm back. So what I did was I threw the microcontroller up in the air over a bed so that it had a soft landing. And now we're about to find out if I actually observed or collected data that showed that it was in free fall, that is zero gravity, for a little while. So let me write a program that will graph the data. So I want to open the file again, as usual. And in this case, I'll actually copy this. I want to repeat until the end of the file, but instead of saying the value, I'm going to graph it. So we'll graph the next line of data. And I'll just clean up a little bit here. Okay, so let's see what we got. First, I'm going to open the graph and make it a little bit bigger. And now I'll run this script that plots the data that we collected. Wow. All right, let's interpret this data. So first of all, we noticed that it kind of wiggled up from a baseline of, who knows, and when it got over 70, it triggered and started recording. So this is me throwing it up in the air. So there's some acceleration as I'm throwing it. At this point, I released it. And you see that we got down to almost 0G as it was in free fall. So this whole flat area down here is the free fall portion. The fact that it's not totally 0G might be explained by the microcontroller spinning or rotating a little bit, which would give it maybe some centripetal acceleration that it was measuring. Then this big spike here is it landing. By the way, I did this over a bed so that it would have a soft landing. So it spikes up as it hits the bed. Then it actually bounces in the air and goes back to 0G for a short period of time. Then it hits the bed again and bounces, and we get this big kind of spike as it hits for the second time. There might be another bounce, but we didn't record data that far. So anyway, this basically shows that the file system is really useful for data collection. Last year at the Robolot conference, we showed the ability of MicroBlocks to communicate over Wi-Fi to Snap or to the Mozilla Web Things gateway. That was using the Mozilla Web of Things protocol. Recently, we've extended the capabilities of MicroBlocks to communicate with HTTP servers and also to implement your own HTTP server. Let's take a look. I'm going to import, for starters, the HTTP client library. Now, one thing you might notice is that although I imported the HTTP client library, I also got another library, the Wi-Fi library, which is the library that allows you to connect to the network. That's thanks to a new feature of the library system, which is that it actually keeps track of the dependencies. So because that library, HTTP client, depended on Wi-Fi, we got both libraries. You'll also notice that in this library dialog, information dialog, you have things like tags, a description, and a version number, also an author. So all of that information is going to make it much easier to manage libraries going forward. All right, so let's take a look at what you can do with this. So the simplest thing you can do is to make a request to a server. So I'll just make this request to the MicroBlocks server. This is an example text file. But let me try a different URL. Let me just try the home page. And here you get the first part of the headers for the home page, the HTML for the home page. So that's pretty exciting, but there's even more. MicroBlocks 0.5 comes with a nice demo program showing how you create a server. Let me go ahead and open that up. It's called HTTP Server. And it has a nice big comment here which says how it works. But before I run it, I have to fill in my network name and password, because all of these Wi-Fi examples require that you connect to a network. So let me go ahead and start the server. When it starts, it tells me its address, which is going to be useful because now I want to actually connect to this server. So I'm going to open up a browser and type that URL that we just saw. I think it was 136. And there we go. We're getting this response from the MicroBlocks server. Let me try a couple of these examples. Let's try test. Okay, there's a test URL. And foo. Okay, a page that says foo. That's cool. And how about bar? So here's a page that says bar, and it includes a reference to the MicroBlocks logo image. So going back to MicroBlocks, how does this actually work? Well, it's all driven by this little set of lists, a list of lists, which initialize this set of responses. So in each item of this list, it's got sort of a list of sublist of two things. So the first thing is the URL to match, or the path to match. So the basic slash generates this HTML, slash test returns this HTML, and so forth. So basically, when it gets a response from the server, it searches through that list of responses, looking for one where the path of the request equals the first item in that response pair. And if so, then it returns it. And if not, then it returns a 404, not found. One of the exciting possibilities opened up by the ability to make your own server in MicroBlocks is the idea that you might make a server that can stream media such as sound, or in this case, image data, from Snap to a Wi-Fi enabled board such as the ED1. This project, or this program, works by waiting for some header files which include the width and height of the image, and then repeatedly, until you've gotten to the height of the image or there's no more data, it draws the pixels as they arrive. And finally, it sends back an OK to the original request. Let's start this up and go to Snap and see how the Snap side works. On the Snap side, we have to encode the image in some way. So this block does that. Notice that I'm scaling the image to fit on the 128 by 128 pixel ED1 screen. The result of that is 36,871 bytes of data that are going to get sent. And they'll get sent as I click this post request. So let's see what happens. And there's the image of myself that just got streamed. We can switch to another costume and repeat that process, encode and send. So you can see it's not instant, but it's pretty fast, and it's very exciting. You can also stream sound from Snap to MicroBlocks. In this project, which I'll start, this works a lot like the image streamer. That is, in the Snap side, we first prepare the data to be sent using this script right here, which is downsampling by a factor of 4 from 44,100 samples per second to a quarter of that. We're also reducing the bit depth from 16 bits per sample to just 8 bits per sample. And the result is a sound file which is 3/4 of a megabyte, which is way more than the amount of RAM that you have on an ESP32 board. Here's the MicroBlocks side of this. This project is a little more complicated than the image streamer because it's doing a little bit more. Right now we're hearing the samples as they arrive, but if you fill in this file name, you can actually store the sound into a file so you can play it back later. That's a pretty powerful feature. We've seen that MicroBlocks 0.5 includes some powerful new features for ESP-based microcontroller boards like the CityLab ED1, including sound output through a digital to analog converter, a flash file system, the ability to write HTTP clients and servers. Those capabilities work together to make it possible to work with rich media in MicroBlocks, including sounds and images. You can synthesize sounds, play digital audio, stream images or sounds over Wi-Fi, or store them in the Flash file system. Those things were not possible before, and we're excited about the creative possibilities that they open up. I'd like to take this opportunity to thank the MicroBlocks team, especially Bernat Romagosa and Kathy Jury, who work with me pretty much every day, as well as those who've contributed code, translations, and feedback to MicroBlocks. I also want to thank the MicroBlocks Leadership Committee, including Jens, Tom Lauwers, and its newest member, Aman Milner. I hope you've enjoyed this presentation and that you're inspired to do something creative with MicroBlocks 0.5. Thank you.